In this video, it's an example problem for 5.3 in AP Chemistry. The unit 5 is kinetics and section 3 is concentration changes over time. And instead of trying to solve for rate laws and rate orders in respect to each reactant by using a data table and comparing trials, now we are going to be using graphs to be able to answer questions and write rate laws. So it's a little bit like 5.2 or section 5.2. It's just now we're doing kind of the same thing with a little bit more ability to solve for more data, but you have to have the graphs. Okay, so the first thing would be you would have to do the graph, or in the problem, they would tell you about the graph, okay? So they'll either give you the graphs or they will tell you that it's a straight line when it's like this. So they said the plot of the natural log of A versus time, and keep in mind A is any reactant that you could have, and B and C are the products. In kinetic experiments, we always monitor the reactant disappearing. And the plot is a straight line for the natural log graph. So what that means is that we know from the notes above, these were in a separate video, we know that this is going to then be a first order reaction, because again, the graph was a straight line when we had the natural log graph. And again, the mathematics of why that is, we won't really be covering in this video. So what that means is the rate law would just be rate. You write the word rate and then equals the rate constant K, and then the reactant, in this case, they're just saying A, and then to the first power, or to the exponent of 1. We can also write the integrated rate law, which is when we're going to have the y equals mx plus b graph, and that's that the natural log of A at any time is going to be the slope of the graph, but the negative K, and then time, and then plus the natural log of A naught. And A naught, remember from the previous set of notes, A naught is the point at the initial of the start of the experiment. And we just took the natural log of it so that it would create a linear graph. So you will kind of need like the notes above to be able to do these problems. All right, next up is what's the value in units of the rate constant? They actually made this an easy question. If they give you the slope of the graph and you don't have to find it, that is the K value, but remember, we don't tack on the negative sign with it. So for the value of the rate constant K, it's going to be, and it's 0.0045, and then per second. But you're going to see in some books they might put it in scientific notation. So 4.5 times 10 to the negative 3, and then per second. So the value of that was kind of just given to you right in the prompt of the problem. And that they told you the slope of that graph. All right, so those are actually two easy ones. The next one is what's the half-life, and so then you're going to need to know the half-life equation, or you could do the integrated rate law, but to save time in this video, I'm just going to use the half-life equation and then the slope. So what you'll do is if they say calculate for the half-life, you just do T1/2 is going to equal 0.693, which is the natural log of 2. And then over K, but we do know what K is, so it's 0.693 divided by 0.0045. And then the half-life is going to be then in seconds. So if you think about it, you have per second here, but that means it's going to come up to the numerator. And when you solve for the half-life for this, it's going to be 150 seconds. And the 2 sig figs comes from the, so you wouldn't want to say more than 150, and you wouldn't want to put a dot either after the 0. Just a quick little sig fig rule here is that, 2 sig figs, we only want to keep the 1 and then probably either round it up or down to the 5, the 50. The other thing you could do is 1.5 times 10 to the 2, and then seconds. So either one of those could be your answer for that. So that one's not bad if you know the half-life equation. The other thing you could do is something similar to what I'm doing here, except for put in 50% of the concentration, meaning you start out with like 1 molar and then it goes to 0.5. But this one, they actually want us to solve for what's going to be the concentration after 225 seconds. So this experiment is running. I'm just going to zoom out to see this graph up here. So this experiment is running, and here would have been about the half-life. I kind of have like a green dot on all of these, but they're just saying after a certain number of seconds, maybe here, what would be the concentration at that time? And because we're using a linear graph, we can solve for anything, like I said, interpolating it, meaning any point on the line, or we could extrapolate like this graph, any point beyond that straight line. Okay, so for this one, we just want to use the correct integrated rate law equation. So I'll just rewrite it for you. So it's natural log of A at any time equals negative KT plus natural log of A naught. And so we're going to find the natural log of AT. Oops. And we'll talk a little bit about a math trick that we're going to use. And then we know that it's 0.0045 second for K. And then the time was 225 seconds later. So those two units will be converted or changed. And then you're going to take the natural log of the initial concentration, which is 0.25. Now, for the sake of time in this video, I'm not going to solve for anything but the kind of the final answer here. So with a calculator, we're going to need to know what this all equals. And after that's done, we're going to take the natural log, e to the natural log, which will then cancel. So whatever this value is up here for everything that is in the above, we will then have to go A at that specific time is going to equal E. So whatever this all equals right here. And if you grab your calculator, it should give you the final answer is 0.09, and then with 2 sig figs we can only keep well, actually I think we can keep it with this one. Actually we can keep an extra one. We can keep 3, and that's the concentration in molarity most likely. And then whatever this number was, I believe this was a negative number up here, but e to that negative number is going to give us 0.0908 for a final answer. All right, so when you plug that into your calculator, just make sure that you take these two numbers and then this number, and they're both negative, and then whatever that total goes here, and then you take e to that number that was up here. I didn't actually calculate it ahead of time. I just know that the final answer is 0.0908. The other thing you might see is this could be written in scientific notation, just a quick little scientific notation, and then to the -2, it would be another possibility. And then because of significant figures, this had 3, this has 3, and then, I don't know, we could actually argue that this could be just 9.1 as a final answer also. All right, so that's kind of how to do an example problem with concentration changes over time, and just kind of using a little bit of your algebra content, you get to apply it to a chemistry problem and solve for concentration at any specific time.